primera persona que va a pasar es el profesor Franz Frechen. Él es ingeniero mecánico, tiene un doctorado en olores y más de 30 años de experiencia en el sector. Si tuviera que definirlo en pocas palabras, es uno de los especialistas de olores alemanes más prolíficos. Por favor, Franz, tu presentación.
Thanks for the introduction, and first of all I would like to express my sincere thanks. It's a big honor for me to be invited to talk to you on this conference. It was already mentioned that I'm dealing with odor since more than 1/3 of a century, and when I thought back now, the real first time I was in South America was 1991, and I was called by an engineer to help with an odor problem in Brazil, in Salvador de Bahia, at a petrochemical complex, and it was really a hard task to deal with that. So it's very nice to be here in Chile again, and we have only limited time. So there's no overview. You see the overview here. We have 3 topics: VDI 3880 sampling, VDI 3885 part 1, sampling for liquid samples, and we will talk a little bit about e-noses. So if you, maybe some of you know the VDI 3880, it is about a little bit more than 2 years old, and there are some chapters. I will only highlight the most important ones. There's a very important one on general requirements on sampling, and there are some quite important settings in this VDI guideline. The one that was discussed very harshly was the sampling duration. In former times, sampling was done by whomever as long as he wanted, maybe only a few seconds or 1 minute or so. Now it is determined that sampling has to take 30 minutes. This is in accordance with the German law concerning clean air, or Clean Air Act's based on 30 minutes sampling time. You have to take at least 3 samples per source and per operation condition, if you can decide between this different operation conditions. So this will be multiplied by the number of operation conditions. Maybe you know also that in the European standard, 30 hours for sample storage are allowed. We restricted this to less than 6 hours. If you want to extend this time, you have to prove that the samples are stable. There's another chapter, performance of sampling in relation of source types, and this is the main part of the whole thing. And we have a chapter on quality assurance. Concerning source types, we have a discrimination between whether we can measure an air volume flow or not. And if we can measure an air volume flow, we have active sources that can be point sources or area sources. And if it's not or barely not measurable, we have passive sources, and these are passive area sources or volume sources. In the European standard, this is called fugitive sources. So these are the examples. A stack is an active point source. An active area source, for example, is the biofilter. This is the most common case. We have passive area sources, and we have volume sources. For example, this sludge dewatering and incineration building. With a point source, you have to obey the rules that are given in the 3880 and also in other standards. This is a DIN standard, DIN 4200, concerning the number of measurement points. If you have an active area source, then this is the scheme that how you have to do it. You have to prevent the ambient air from disturbing your sampling. So you can either totally cover or you can choose a hood. Concerning the question, hood or total cover, basically a complete cover is more advantage, because there you have a very good determination of the total odor flow rate. So because you get the whole flow, you can easily determine the total flow rate. But there are also disadvantages. This is just an example of a small biofilter. Of course, you cannot do things like this with a very large one. In that case, you have to resort to the hood method. And also the hood method is beneficial if you want to know more about the biofilter in itself, whether it is inhomogeneous, whether it has some gaps or whatever. So in this case, it's better or necessary to use the hood method. And the decision whether you have the hood method or the complete cover is on one hand depending on technical possibility, and of course it is to be answered according to the question that you have to answer with the result. These just example for a hood of 1 square meter that you have to place on several points of, let's say, a biofilter. And the number of points you have to sample on is also given here. You have these stipulations that you also find in the documents on your USB disk, USB stick, and you see that we have at least 10 square meter representing, and if you have very small area sources, you have to have at least 4 samples. More problems arise if you have a passive source, because you don't have a really measurable outward airflow. Like you see here, this is a hazardous waste landfill. It stinks absolutely, but you cannot measure any airflow here. Or this is a compost heap with aeration from the bottom. And this is my profession. It's a wastewater treatment plant, and this definitely you see is a passive area source. But the other part of this one, you see there is an intensive aeration, and the question is this still a passive area source, or might this be an active area source? And the decision is made by convention in the VDI 3880 with 30 cubic meter per square meter an hour. If you are below that, you should use a flow-through hood. If you are above that, you have an active source. We discussed the active source already, complete cover or sampling hood. Biofilters usually are designed with 30 or even more, usually today much more than 30 cubic meter per square meter an hour. If you look for standard aeration tanks, you will find that we are much below this, but there is still an outward airflow. You can measure this by just checking the blower that blows the air into the aeration tank. So what do you have to do in case of a passive area source? You have to use a flow-through sampling hood. And this is a scheme of what we do. We just cover part of the area and send clean air through this sampling hood, and we get out polluted air, and we can measure this thing. What we have is the surface covered by the box, by the sampling hood in square meter. We know the flush air volume flow in cubic meter per hours, and this gives the flushing rate in cubic meter per square meter an hour. We measure the odor concentration after the sampling hood, and this gives us the odor units per cubic meter, and this gives the area-related odor flow rate in odor units per square meter an hour. And this is the only number concerning passive area sources like wastewater treatment plants or landfills or whatever. This is the only number that can be used for comparison of different types of processes. Everything else is rubbish. If you have the total emitting area in square meter, you can get the total odor flow rate in odor units per second or per hour or per whatever time you would like to choose. And as I mentioned, only these numbers, especially this one, are of importance. In former times there were some other things, but nowadays this is the only thing. This is from former times. Maybe someone has seen this device. It's a Lemberger box. Here you have a small activated carbon filter, and this is a compost heap. Incredible things at that time. Now it changed a lot, and when we elaborated the VDI guideline, in order to decide about design of this flush-through sampling hood, we made test comparison with several types that were on the market at that time at a wastewater treatment plant. This is one type with a very high flow rate, flush rate going across this very small area. And this is, here, that's it when it's launched. And there are other ones. This one is a famous Spanish one. This is a famous German one. And so we made comparison with these measurements and finally came up to a general scheme like this. We don't have a labyrinth inside. It was discussed to have a labyrinth inside to increase the speed over the surface, but we didn't decide for that. dimensions are given in the next slide, and this is just a cross-section telling the principles of a sampling hood like this. And the dimensions that are set in the guideline are 1 meter by half a meter and 30 centimeters high. And, of course, an area-specific ventilation rate of 30 cubic meter per square meter an hour. And if we work at the borderline between flow-through hood and other ones, we operate with this 30 cubic meter per hour. So it's absolutely necessary that this exactly matches the criterion which type of sampling device you have to use. And if you have, by chance, an aerated source that exactly produces 30 cubic meter per square meter an hour, in theory, you wouldn't feed any fresh air into your sampling hood. So that's the decision. This guideline you will not find so far because it's not issued right now. It will be issued, I think, in 2 or 3 months for public comments, and I hope that we will get it ready and issued by this year still. This is olfactometry measurement of the odor emission capacity of liquids. And this is one of my favorite hobbies since a long time. If you look for the emissions, maybe you have enterprises that have emissions directly into the air that you have to sample correctly according to 3880, of course. But you also have wastewater industrial discharge into a sewer. You have municipal discharge into the sewers, and then in the sewer you might have septicity, anaerobic degradation, and sulfide formation, because we have enough sulfate in every drinking water. As an average in Germany, 60 milligram per liter, and this easily is converted in anaerobic processes to sulfide, of course, and this causes H2S emissions. So if we look for the real origin of the odorants, it's definitely the liquid. From the liquids, the odorants go into the sewer air. From the sewer air, they go into the ambient air. And if there's someone living in the ambient air, he has a nuisance. But basically, if you look for the real source of the problem, you have to look in the liquid. Example, you have a very laminar flowing, slow flowing sewer, which has a high content of odorants. You will not notice this in the atmosphere above the wastewater. But after maybe 2, 3, 4 kilometers where you have a drop and an increase of turbulence, you will find a big release of odorants at this drop. And then all people say, well, what's happening at this point? Is there something specific with that point? That's not the origin of the odor. The odor is much farther upstream. And to detect where you have the really origin of the odor, you need to know about the odor concentration in liquids. The definition is very, very easy. The odor emission capacity of a liquid is the total amount of odorants present in the liquid that can be stripped from this liquid under standardized conditions. It's not what you strip from, let's say, a wastewater in the sewer system at any given point. It's the maximum strippable amount of odorants. And the unit is exactly like we have with olfactometry. We have odor units per cubic meter, but not per cubic meter of air. Instead of that, per cubic meter of liquid. And as I mentioned, I hope that we will have it finalized in 2014. As we strip off, we said we strip from the liquid, so we produce air samples, and these air samples can be measured. The quantification is be done according to CN 13725, of course. But what is done prior to using this standard is the stripping test, the OEC test. And this is the OEC test reactor as it will be prescribed and defined in the guideline. We have a liquid sample of 30 liter. We have a headspace less than 15 liter. We have a fine bubble aerator at the bottom. We have odorless air stripping the odorants to the top. And here, from time to time, we take air samples and bring these air samples to an olfactometer. And if we discuss about stability of the liquid sample and the air samples we produce, the air samples we produce are much more stable than the liquid is. Usually liquids are biologically highly active, and especially if you irradiate them, you will even improve activity. So it is absolutely necessary and important to do the sampling of the liquid sample and the test immediately after each other. And that's the reason why we at my department built a trailer where we have 3 of these devices, so we can do 3 tests on site in parallel, and then we have air samples that we can store for, let's say, 6 hours, like VDI 3880 says. So what happens? How do we evaluate the result? This is the result of the first sample. Of course, it's the most smelly one. This is the second one, the third one, and so on. And the odor units per cubic meter of liquid is nothing else than the area below these measurement curves. So just an integral of this area. In your documents, you find how to evaluate this more in detail. I won't tell it too much in detail. The OEC total, that is what we can measure here, is in this case identical with the OEC measured, which is the blue area. In the documents, you will find the two other methods and 2 other possibilities. So there you can get the odor units per cubic meter of liquid. A thing that is very important is keeping sewer systems free of odor. And many cities spend a lot of money dosing chemicals into their sewer system. Paris, for example, doses just the plain chemical cost between 3 and 7 million euro per year just to suppress odor. And the question, of course, is it overdosed? Is it underdosed? Is it efficient or not? With the OEC method, we could easily detect whether it would be overdosed or underdosed, and if we would have this method online, we could even make a closed-loop process control to save dosing costs. And this is what we have done at the department. We built an automated version, a small automated version of the whole test. You see this here. That's the second and third sulfide and odor measurement piece. At this moment, we are, with the city of Hanover, trying to have a much more simple device than this one. This does OEC automated. And this one, where you see the reactors are much bigger than you have seen before. This one was made specially for Berlin because they wanted to do a lot of research with 4 different e-noses behind these things. Because if we want to do it online, we cannot use olfactometry, we cannot use test persons, we have to find something which can give an online signal, and these are electronic noses. In the project Berlin, we had 4 electronic noses to test. And so that's the reason why we always have to connect it with electronic noses. A perfect e-nose would be able to measure the real odor concentration, but we don't have a perfect e-nose. This means we need a mathematical model that converts the 4 to 10 sensor raw readings into one number, which is the real odor concentration. We will come back to the real odor concentration in a second. To establish this mathematical model, and mathematics is the most severe thing with electronic noses, you need parallel measurements with e-nose and from the same sample with olfactometric data. And the more parallel readings, the bigger your sample is, the better is your mathematical evaluation. This is the data pool we have right now with more than 2,500 samples. I think if anyone knows any lab in the world or any research institution that has more parallel readings between e-noses and olfactometry, please tell me, but I think this should be the largest data pool worldwide. So what can happen with data like this? We have several sources of problems and errors. Sampling, I don't want to deal with that. Uncertainty of olfactometric measurement. We have to differentiate between the real odor and the odor measured by olfactometry, because you all know olfactometry has a certain error and certain error in itself. And if you listen to Berger, he says, well, the error of olfactometry is about 50%. This means if an e-nose would perfectly explain the odor that we measure at the olfactometer, this model would have an error of 50%. So this just to keep in mind. And there are more possible problems. One of the possible problems also is the e-nose itself. The T90 time, which is the time until 90% of the final value in the signal is indicated, No one of the electronic nose manufacturers tells you about that. They can't do it. It's impossible, because maybe some sensors have a very good behavior and they have a final value. Others don't go to a final value. We have oscillated readings, but here we can use means. We can ask the question, do two e-noses of the same brand, of the same type, of the same age deliver the same reading with the same sample? And here you see one of our tests. And you can talk about aging of sensors. You can ask, do these two e-noses, 1 and 3, which are new, and the e-nose 2, which was a little bit older, 2 years older, give the same reading? You see, this is not the case. So these are all possible problems that you could come again when you work with e-noses. And also the odor's nature is a problem in itself. Cocaine solo gives a different view than cocaine mixed with beer, of course. But the most important thing with e-nose is a mathematical evaluation. This is a crucial step. There might be two aims, basically. The qualification, which kind of smell is that? This might be pattern recognition with different types of mathematical method, and quantification with different types of mathematical artwork. And if we deal with quantification, this is what we need for our online OEC measurement, because we want to have something like the odor units per cubic meter of air. We have to look for quantification. And also the mathematics can kick you off. Just one example out of many. If you have a very small mathematical data sample, and if you have basically a nose with 10 sensors and you choose only 10 or 11 or less pairs of data, you will nearly in any case get 100% correct explanation, which is a mathematical artifact. But the most important thing is that usually if vendors of electronic noses give a model and say, our nose explains odor as it is, they only explain historical data. But this is not what we want. What we want with an e-nose is we want to predict if the next set of raw data comes in. We want to, without having olfactometry, we want to be sure that the model calculates the correct value. So it's not important to explain your data very good. It's most important to have a model that can forecast, that can predict the next incoming set of raw values. And this is what I call prediction ability. And in order to test this with a set of data you have to split your data. You have to use the bootstrap method. You have to split your data. We could discuss a lot about splitting your data. You can do it 50 by 50%. If you do so, and if you have 20 values, you have several hundreds of billions of possibilities how to split. But basically, you split your data in one thing and get an explanation of 50% of the data like this. That shows a quite good correlation. But if you use the model derived from this set of data to work on that, on the other 50%, you will see a result like this. So this is a model which looks very funny and looks very good, but which is not able to predict very precisely. So if you deal with e-noses and if you deal with mathematical evaluation, ask the guys always, do you only explain your historical data set, or do you do bootstrap method and do you predict your data? And that was it. Thank you very much.
They should recalibrate an electronic nose.
Well, I have a tool. This is mathematics. But I have no insight in what all these manufacturers do. This you have to ask your manufacturer. You can ask him, for example, what quality management system is applied to production of the e-nose concerning the sensor, type of sensor. Is each sensor tested to be in a certain range of accuracy? Ask the manufacturer what they do for quality assurance. That's a very important thing. And the best thing, if you think about buying 10 or 100 e-noses, which could be an interesting thing for large areas, would be to have a visit and stay there for some days and look what they're doing.